Saliwat, no? So we are now recording our lecture. So we have now continuation of our topic last time. No? So this is about electric charges still. No? But let's look at other nature, other characteristic of these electric charges. No? So we will look into this principle now, maybe formulated by one of the individuals who made some serious study on charges, no, and it is Charles Coulomb, no. So we'll be looking at the contribution of Charles Coulomb, no, and I believe, no, we will encounter that word Coulomb as a unit of our charge also, no. So because of his major contribution, no, his name or family name or no, ginhimo siya, no, made into a unit of electric charges, no. So an electric charge is another quantity now which we could not include or incorporate to velocity, to length, no, to time or to mass. So therefore we have to create a new one. No? So we have now Coulomb's law. No? So Coulomb's law, after the famous scientist, no, in the 18th century, he is a French scientist, Charles Coulomb. No? He studied about forces, no, that exist between two given charges. So whether the charges are of opposite, no, opposite sign or opposite charge, no, like positive or negative, or whether they are of the same charge, no, or the same sign, like positive and positive or negative and negative, no. So these forces, no, according to the basic law of electrostatics, will either have an attractive or repulsive force, no, that will be existing between them, no. Others would pronounce the name here, no, as Coulomb, no. So others would pronounce it as Coulomb, no. But there are physicists who will make sound of it as Coulomb, no. So what is this Coulomb's law, no? So in mathematical form, no, the Coulomb's law is written this way, no. So there is a certain constant K, and K now is a value that we will probably encounter there later. So it's a constant value of proportionality. I think they call it as permittivity constant. And the other one is this Q values, no, above. So usually Q is denoting a charge, no? So there are two charges that are involved. And then there's R here below, which represent the distance between our charges, no? So any given two charge, no, for example, we will have these two charges here, no? So maybe one of them is a positive charge, and usually they denote these charges with letters Q, no? So maybe this is Q sub 1 or Q, no? Then it's a small letter, a small number, no? And then you have here Q sub 2, no? So these are charges, no? So either Q sub 1 and Q sub 2 are the same in sign or they are opposite in sign, no? And then other than that, they are separated by a distance, no? So there's a distance between them, no? Oh, sorry. Let us redraw this. So again, there's a distance between the two charges. And we usually call it as R, no? And supposedly we are to call it as D, diba? That's a distance, no? But usually we call it R because it's a radius of curvature, no? So that's the distance between the two charges, no? So either the two charges are of same sign or they are of different sign, no? So either this is a negative charge or the other one is a negative or a positive charge, no? Depende, no? Depending on the kind of charge that you deal with, no? So maybe we could have a positive charge here, no? and the other one is a negative charge. So depende, no? So if they are of different signs, then they tend to attract each other. No? Now, according to this equation, no, Q1 and Q2, no? And Q sub 2, these are your charges. And R here is your mean distance, no? Probably that's your mean distance between the charges, no? These are factors that affects the amount of force. So F here is our force. So it's either attraction, either the charges are attracting each other or they repel, depending on the kind of charge that you deal with, no? So usually the unit of our force is of course in Newton, no? So our charges, no? The unit of our charge, it's in Coulomb, no? Our force is of course, no? Unit of the force that we deal with there is in, so Coulomb is in the SI or in the metric system, no? Now our unit of distance is of course is still in meter, no? So the mean distance there is in meters, no? So again, we can either call this as the mean distance between the charge or the radius of curvature, no? That's why they use the symbol R, no? Well, that's with, no, our equation. So Charles Coulomb formulated this, no? And the force here, no, according to this equation, no, are affected by the two charged objects, no, on one another, and the product of these charges, the magnitude of the charge, no, is proportional, no, to the value of the force. But according to this statement, it is inversely proportional to the square of the distance between them, no? So there's an inverse relationship, inverse proportionality, and a direct proportionality relationship, no? So according to this one, the product of the charges Q1 times Q sub 2 is directly proportional to F, no? Meaning, as we increase the value of the charges, then force increases. However, the distance between them is inversely proportional, meaning if the denominator is increased, then the force eventually decreases. That's what we mean by an inverse uh, relationship, no? Okay, so we have, no, our Coulomb's law, no, nga principle, no? And let's go into, no, the repulsive nature of the charge, no? So if they are both positive, Q1 and Q2 are both positive, then they will tend to push each other, no, away, no? If they are, again, no, same negative charges, then they will tend to push each other also away, no? But if they are of opposite signs, no? So opposite charges will tend to attract, no, each other. So the F there is either attraction or they can also be repulsion, no? Now, again, no, the unit of our charge is known as Coulomb, no? A Coulomb is the amount of charge that moves past a point in 1 second, no? So if you have the value of Q is equals to IT, no? And we will encounter later what is this I, no? And I, according to this expression, is known as ampere, or we call it as current, no? Current. So the amount of the charge, no, and as it passes in a second, then that's what we mean by a coulomb, no? Now the value of K that we saw earlier, no, is equals to 9 times 10 to the 9, no? Newton meter square, no? That's the value equivalent to K, no? So K being a constant, no? So again, if we replace K here with a constant, then it's a steady value, whereas Q1 and Q2 will depend on what you have, no? What you have as a value, no? So, for example, no, using the equation above here, no, the Coulomb's law, uh, it can be seen that two equal charges of 1 Coulomb separated by a distance of 1 meter will exert a repulsive force, no, equal to 9 times 10 to the 9 Newton. No? So this value is a very big value. No? Ang imo charge ko, no, that charge is merely, no, 1 Coulomb each. No? So if Q1 is 1 Coulomb, Q sub 2 is also 1 Coulomb. The distance between the two charges, no, supposing the two charges are equal to 1 meter away, no, they are 1 meter away from each other, then they will push each other, no, a value equals to 9 uh, giganewton. No? And we know giganewton is a very big number. No? So that's how strong is the electric force here. No? So this is a kind of an electric force that pushes the charges, no, against each other. No? So that's a very big quantity. No? So therefore, no, a 1 Coulomb of charge is a very big charge. No? So usually the value of our charge, guys, no, is not in Coulomb, no, directly, but we use the um, what do you call this, suffix, no, a prefix, micro, no. So commonly our charges are in micro Coulomb or pico Coulomb, no. So maybe you could also have nano, no. So we have to have a very small amount of the charge, because if we will deal exactly with 1 Coulomb, no, of charge, then the force there is too big. No, that's a very, very strong amount of charge. No, so therefore you could not keep them, no, near each other. No, so just imagine, no, 9 giganewton of force. No, so that's a huge force. No, so again, typically what we deal with, no, are smaller units of charges, no, which are expressed in micro. So this is mu, and mu is in 10 to the negative 6. No, pico is negative 12, no? And nano is 10 to the negative 9. No? So these are our expressions of our charge Q1 and Q sub 2. No? Now here's an example, no, of our Coulomb's law. So finding the value of the electric force. No? So if we call the electric force there as F sub E, then the force between two positively charged bodies, no, is equivalent to this much of Fe. Now, again, K being 9 times 10 to the positive 9. No? So if we substitute the values of our charge, no, again, two charges, no, have equal magnitudes of negative 10 to the negative 6. No? So this is uh, micro. No? So this is in micro Coulomb. No? So usually if you multiply the exponent, if we deal with an exponent, no, that there are then you multiply two values with exponents, then you will be adding their numerator. No? So negative 6 plus negative 6 is negative 12. No? Now, if you multiply it with 10 to the 9, no? So this is positive while you have negative 12. No? So 9 minus 12, 9 minus 12 gives you negative 3. No? Okay, so you see the outcome. No? So basically, we can also write this as negative 1 times 10 to the minus 6. No? When you write this in your calculator. No? So 10 to the minus 6 can be written as 1 or negative 1, since the sign is negative. No? So these are negative charges. So negative 1 times 10 to the minus 6. No? And then this one is also the same. No? So that's another way of writing our value here. No? So we will end up with 9 times 10 to the minus 3, or this is a milli-nano. No? A milli-newton. No? So 9 millinewtons of force will exist between these two negative charges. Ano ni siya? Attraction or repulsion? What is this kind of force that will happen here? Attraction or repulsion?
Traction, sir.
This will be, no, this will be, why do we say repulsion? Why will they repel? Because they are of the same sign. No? They are both negative charges. No? So negative and negative, same charge, a same sign, they will repel. No? So the product of negative times negative gives you a positive force. So a positive force basically is a repulsion. If one is positive, the other one is negative, then the product of a positive and negative becomes negative. So a negative force is actually probably an indication that they are attracted to each other. No? So, so the amount of force here will be dependent on this value. So maybe if you'll try to draw this, so you may have this charge here. These are the two charges that you have. And again, Q1 or Q sub 1 is equal to negative 1 times 10 to minus 6. That's 10 to minus 6 Coulomb. And the other Q value, Q sub 2, is also negative 1 times 10 to minus 6. That is still in Coulomb. Now, the distance between them is, again, the distance between our charge. So, R is 1 meter. I think that's 1 meter. So 1 meter distance. So again, if you substitute this value, then again, this is what we end up with. So negative times negative becomes a positive charge. Okay, so they are both negative charges na sila. So they are both negative charges. So let's check another expression or another value here. So this is our Coulomb's law. And again, K is 9 times 10 to the positive 9. So there's a number here now where you can probably try another expression. So maybe you can apply it there. How much is the electric force? So there's an electric force here. How much the electric force that exists or is separated by the distance of 2 millimeter. So when you write millimeter in meter, so that's 2 times 10 to the negative 3. Milli is 10 to the minus 3. So you have to convert the distance in terms of a meter. Now our electron is ang iya value, that's a very small charge. And it's equivalent to 1.610 to the negative 19. And again, being an electron, you can probably consider that this is a negative charge also. Now again, now we can answer this maybe sometime, maybe later on. Now, conductors and insulators, So, conductors are materials that allow the electricity to flow or charges to flow, Whereas, insulators are those that prevents the charges from flowing, So, conductors are good, they allow the passage of heat, At the same time, they allow the passage of charges, So that's the nature of conductors, So they conduct both heat and electricity. On the other hand, insulators prevent charges from flowing from one conductor to another. So like you're working with electricity, you have to have a tool, you have to have an equipment that has a very good insulation. So you don't forget to use like a plier or a screwdriver that has a good insulation when you're dealing with live, or there's the presence of electric energy in the wire, no? Or else, no, if you forget that, then maybe, no, you'll get electrocuted, no? Now, electric cords are insulated to prevent the flow of electric current to our hands, no? Electricians use rubber gloves, no? So when working with electricity, no? Usually, the other word that they use for insulators are, sometimes they use also the word dielectrics, no? So dielectrics usually are materials that are able to be charged, no? So we learned last time that plastics, rubber, no, glass are materials that are capable, no, of being charged, no? Sometimes they call it, no, dielectrics, no? So dielectrics are materials, no, that can be charged, no? So again, no, it resembles similar to our, no, insulator, no? So no? And then usually, no, materials that are difficult to charge are sometimes called also as non-dielectrics, no? Now dielectrics, no, we talk about dielectrics because these are materials that are used, no, in some capacitors, no? So we will go into the uses and the importance of this device called capacitors, no? So again, no, insulators are good materials, no, that can be charged, no, and again, no, since they prevent the flow of electricity or charges, then you can work safely when dealing with, no, a live electrical wire, no. Now, if we have here, no, charges that are arranged in this way, you know, so forces acting on a system of charge, and we are given a diagram below, no. So charge A is 1 microcoulomb, no? So this is how they are arranged, no? Maybe they are spaced equally apart, and you can talk of this, or you can imagine this as an equilateral triangle, no? So there are the sides there, or distances between the charges, they are 1 meter apart. Now we realize that we can get the force, no, that exists between, no, between charge A and charge B, no? The same way, there's also a force that exists between charge A and charge C, no? So with regards to charge A and charge C, no, there's going to be a force here, no? And if they are both positive charges, no, since the sign of 1 microcoulomb, no, is indicated without a sign, so we will assume that it is positive. So A and C will repel, A and B will likewise repel, no? So maybe the force here is going right here, no? This is the direction of the force, no, between A and B, while A and C will have a force that will be directed in this way, no, since they will repel each other, no. But if it's going to be an attraction, maybe this one will be going down, no. So instead of being pushed up like that, maybe this one will go down if B is a negative and this is a positive charge, no. So they will tend to have a, no, an attraction here, no. Now, with respect to charges B and C, no, you'll see that there are two forces here involved, no. So maybe we can call this force here, no, on the left side as F1, no, and on the other end, no, maybe I'll just write it like this, no. So I'll have here F sub 2. So F sub 2 is the force between, no, F sub 2 is the force between A and C, no, charge, no, and they are repelling. So F2 is going upward but somehow pointing left, no? F1 is pointing up still but pointing somehow to the right, no? And if you're going to draw a line here, no, if you'll draw a particular line, no, somewhere here, then you'll notice that these charges are creating an angle with respect to this line, no? And then therefore, no, we will see that these forces here will have a net force, no? So since you're dealing with two forces given a particular angle, no? But our question, how many degrees do you think is this angle, no, creating, no? How many degrees is this F1 creating with this horizontal line, no? Now you'll see that if this is an isosceles or in an equilateral triangle, the angle inside, no, the angle here, you'll probably agree with me that this must be 60 degrees, no? Why 60 degrees? Because the whole angle inside an isosceles triangle is equal, no? That must be 60 degrees. And if you are dealing with an triangle with equal sides, then all of these angles here are 60 degrees equally. So 60 times 3, no, ang 3 corners is equals to 180, no, which is true for any triangle, no? Now, if this line here, no, the horizontal line below, no, and this line, no, are parallel, then if you cut it with a line, we call it a transversal, then the angle here must be equal to 60 as well, no? We call that angle as corresponding angles, no? So for triangles, guys, no, or for lines that are parallel, it will have the same angle, 60 degrees. No? So this is 60 degrees, and the other side must be 60 degrees as well, no? Okay, so 60 degrees na, no? So if you have an angle with